the Einstein equation. Here it is. G mu nu equals 8 pi g over c to the fourth power times t mu nu. So this is sometimes referred to as Einstein's equation. Sometimes it's referred to as the Einstein equations. Let's take a look at what we have. These coefficients, first of all, g is just Newton's constant. C is, of course, the speed of light. Then on the left-hand side, we have this tensor, G mu nu, which is the Einstein tensor. And remember, the Einstein tensor is defined as the Ricci tensor, R mu nu, minus 1/2 the curvature scalar times the metric, G mu nu. So here R mu nu is the Ricci tensor, and it's defined as the contraction on the first and third indices of the Riemann tensor. And the curvature scalar is just the contraction of the Ricci tensor. Now what about this tensor on the right-hand side? This is something new. This is called the stress energy momentum tensor. So T mu nu is the stress energy momentum tensor. Sometimes I'll abbreviate that as SEM. And because this is a lot to say, people sometimes just call it the stress energy tensor or the energy momentum tensor, or even just simply the stress tensor. And what this tensor contains is all of the information about the energy, momentum, and stresses in the non-gravitational fields. Contains all the information about the stresses, energy, and momentum of the non-gravitational fields. And sometimes I'll refer to the non-gravitational fields as matter fields. Let me give you an example of a stress energy momentum tensor. For the electromagnetic field, we define the field strength tensor, F mu nu, and this is an antisymmetric tensor, so it has 6 independent components, and those independent components are the electric and magnetic fields. And then the stress energy momentum tensor is defined as follows. This is in SI units. It's 1 over mu naught, that's the permeability of free space, times F mu alpha, F nu beta, G alpha beta, minus 1/4 F alpha beta, F alpha beta, G mu nu. Let me give you another example. This example is very important in general relativity. This is the example of a perfect fluid. So a perfect fluid is a general model for matter, and what makes it perfect is we're assuming that there's no heat conduction and also no viscosity. So the only properties that the perfect fluid has is it has a mass density, which we'll denote by mu, and it has a pressure, P. And of course the fluid has a velocity. So here's a space-time diagram. These are the flow lines of little packets of fluid. So at each point in the space-time we have a forward velocity of the fluid packet that passes through that point. And I'll denote that forward velocity as u sub f. So we have a vector field, namely the forward velocity of the fluid flow lines. So the other property a perfect fluid has is a velocity u sub f. And then the stress energy momentum tensor for this perfect fluid is defined as follows. It's T mu nu is equal to the mass density times u mu sub f, u nu sub f, plus the pressure times the metric g mu nu plus u mu sub f, u nu sub f. So we now have two examples of stress energy momentum tensors, namely the electromagnetic field and the perfect fluid. And of course, if we had a space-time in which we had both electromagnetic fields as well as perfect fluids, we would just add together the stress energy momentum tensors for each of those fields to get the total stress energy momentum tensor. Now, I'm going to save the detailed interpretation of the stress energy momentum tensor for a later lecture. Detailed discussion of the stress energy momentum tensor. For now, there's just one important result that I need to use, and that is the energy density. So this would be the energy density in the matter fields as seen by an observer with velocity u mu is given by, we'll call it rho, for the energy density, the energy per unit volume, is equal to T mu nu, u mu, u nu. So the stress energy momentum tensor contains all of the information about stresses, energy, and momentum for the non-gravitational fields. And this is how we pick out the energy density part of the stress energy momentum tensor. And of course it's observer dependent. It depends on who's observing those non-gravitational fields. And that dependence appears here as the forward velocity of the observer. Let's apply this definition to our two examples. First, the electromagnetic field. And to keep things simple, let's assume we're working in flat space-time with Minkowski coordinates. And in that case, the components of the electric field are related to the components of the field strength tensor by EI is F0I, so that's E1 is F01, etc. And the components of the magnetic field are just given by 1/2 the alternating symbol IJK, FJK. So in other words, B1 is F23, B2 is F31, and so forth. Now, these are the electric and magnetic fields as seen by an observer who's at rest in these Minkowski coordinates, at rest in this Lorentz frame. So we'll take for our observer the forward velocity is just 1, 0, 0, 0. So we can think of this observer as traveling right along the t coordinate axis in the Minkowski coordinate system. Now let's insert this into our definition for the energy density. So we have rho is equal to the stress energy momentum tensor, that's 1 over mu naught, the permeability of free space, times F mu alpha F nu beta G alpha beta minus 1/4 F alpha beta G mu nu times u mu u nu. And because the zeroth component of u is 1 and the other components are 0, that just converts the mu and nu in here to 0, the index 0. So this is 1 over mu naught f0 alpha f0 beta g alpha beta minus 1/4 f alpha beta g0 0. And of course, the metric here is the flat space-time metric eta alpha beta, just minus 1, 1, 1, 1 down the diagonals. So let's look at this term. We have a sum over alpha and beta, but whenever alpha or beta is equal to 0, that term is 0 because, remember, f is antisymmetric. So we have non-zero terms only if alpha and beta are equal to a spatial index, I or j. And remember, the ij part of the Minkowski metric is just Kronecker delta ij. And we can rewrite this as minus f upper 0i times minus f upper 0j times Kronecker delta. When we raise the zero index, we get the minus sign because of the minus 1 in the eta mu nu, the Minkowski metric. And raising the spatial index is done for free, so to speak, because the spatial part of the Minkowski metric is just 1, 1, 1. So when we raise the zero index, we pick up a minus sign here, another minus sign here. And of course, I can lower these ij indices for free because, again, the Minkowski metric and the spatial part is just the identity matrix. So this is, the minus signs cancel, and this is the electric field EI, EJ, delta IJ, or the square of the electric field vector. A similar analysis of this factor gives 2 times the square of the magnetic field minus 2 times the square of the electric field. So if we put that together, we have rho equals 1 over mu naught times, from here we have e squared, and from here we have minus 1/4, and g00 is minus 1, so we'll make that a plus 1/4, times 2b squared minus 2e squared. And simplifying that, we have 1 over mu naught times e squared minus 1/2 e squared, that's 1/2 e squared, plus 1/2 b squared. Now, we can pull out the 1/2, and if we had gone through this analysis carefully, keeping all the factors of c, the speed of light, we would actually find this is 1 over mu naught times c squared e squared plus 1 over mu naught times b squared. But the speed of light is related to the permeability of free space and the permittivity of free space, that's epsilon naught, by this relation. C squared is 1 over mu naught epsilon naught. So this is permeability, and this is permittivity. Right, so this combination is actually epsilon naught. So what we have is the energy density is epsilon naught e squared plus 1 over mu naught b squared. And this, of course, is the standard result for the energy density in the electromagnetic field. Now let's look at our second example, the perfect fluid. And again, let's consider flat space-time with Minkowski coordinates. So here's our diagram, and the observer is moving straight up the t-axis with 4 velocity u, and the fluid has 4 velocity u sub f. And in these coordinates, u mu is just 1, 0, 0, 0, and uf can be written as gamma times 1 comma v, where v is the velocity of the fluid as seen in this frame. The velocity of the fluid is seen by this observer. And of course, gamma is 1 over the square root of 1 minus v squared. So now we can write the energy density as seen by this observer. It's the stress energy momentum tensor for the perfect fluid times u mu u nu, and this is the mass density times u of the fluid, and since I have the indices down here, I'm going to put the little f for fluid as a superscript. So this is u mu for the fluid, u nu for the fluid, plus the pressure times g mu nu plus u mu of the fluid, u nu of the fluid. So that's the stress energy momentum tensor times the forward velocity of the observer, u mu u nu. So if we multiply this out, what we find is the mass density of the fluid times u sub mu of the fluid, u mu of the observer, and so that's the inner product of u of the fluid with u of the observer, and we have two copies. We also have u sub nu f multiplied u by u sub nu, so there's two copies of that, plus p times, this just gives the inner product of u with itself, and then we have once again two copies of u inner product between the u of the fluid and u of the observer. Now this inner product is gamma 1 comma v. We have the metric minus 1 1 1 1 down the diagonals, and then u is just 1 0 0 0. All right, so if we multiply these two factors, we have, well, first gamma times 1 comma v, and then this gives minus 1 0 0 0, and multiplying that together we just have minus gamma. And of course the inner product of u with itself is minus 1. So if we put all this together, we find the energy density is mu times minus gamma quantity squared, that's just gamma squared, plus p times minus 1 plus gamma squared. And now this combination is gamma squared is 1 over 1 minus v squared minus 1, and I'll write 1 as 1 minus v squared divided by 1 minus v squared. So we have a common denominator. Now this 1 cancels this 1, and we're left with v squared over 1 minus v squared, which is gamma squared v squared. So our result is the energy density is equal to the rest mass density times gamma squared plus p times gamma squared times v squared. Now, if we were to carry out this calculation more carefully, keeping all the factors of c, the speed of light, what we would actually find is the energy density is gamma squared times rest mass density times c squared plus the pressure times v squared over c squared. So you can see that when the velocity of the fluid is much smaller than the speed of light, the energy density is dominated by this term, and this is just the rest energy density. So it's just the rest mass per unit volume times c squared. Let me expand on this observation a bit. The stress energy momentum tensor is mu times u mu of the fluid, u nu of the fluid, plus pressure times g mu nu plus u mu fluid, u nu fluid. And the energy density of the fluid is seen by some observer with forward velocity u is t mu nu, u mu, u nu. And in these coordinates, we see that that's just t0, 0. And what we found above was that rho is dominated by the rest energy. So rho is approximately mu times c squared. So to within factors of c squared, t0, 0 is approximately mu. Now where does this come from? If we look at the full stress energy momentum tensor, what we're doing is we're approximating the velocity of the fluid at the ordinary velocity as being very small. So the forward velocity of the fluid was gamma 1 comma v, and we're letting v be much smaller than the speed of light, So u mu is approximately 1,000. So now if I set the indices mu and nu equal to 0, then this term is just mu. Here we have p times, this is minus 1 plus 1 cancels, so we're left with just t00 is approximately mu in this limit where v is much less than c. Now what about the other components of the stress energy momentum tensor? For example, let's look at the 0I component. So mu is 0 and nu is one of the spatial coordinate indices, I. Well, in that case, u sub I for the fluid is approximately 0. So this term and this term are approximately 0, and also since the metric is diagonal, it's just the Minkowski metric, this term is 0. So this is approximately 0. Now let's look at the space-space components of the stress energy momentum tensor. Well, the space component of the fluid forward velocity is approximately 0, so that means this term and this term are approximately 0, and all we're left with is p times gij. So this is approximately p times gij is just delta ij in these coordinates. But for ordinary matter, P, the pressure, is usually much smaller than the rest energy density. So with this assumption, we see that each of the space-space components of the stress energy momentum tensor is much smaller than the 0,0 component. And now if we put this together, we see that for ordinary matter with velocities much less than c and pressure much less than the energy density, that the stress energy momentum tensor satisfies T00 is approximately mu, and all of the other components are approximately 0. So the stress energy momentum tensor is dominated by this 0,0 component, which contains the rest mass or rest energy of the material. Even though we arrived at this conclusion by analyzing the stress energy momentum tensor in flat space-time with Minkowski coordinates, this holds more generally due to the principle of equivalence. So all we need to do is make sure that our coordinates are closely aligned with the material flow lines. So here's the material world lines, and here are the x0 coordinate lines. So we need to ensure that those are close so that the velocity of the material as seen by an observer moving along one of these x0 coordinate lines, that ordinary velocity is small compared to the speed of light. And if that's the case, then the dominant rest energy part of the stress energy momentum tensor will appear in the 0,0 component. So the principle of equivalence tells us that this result holds in curved space-time, assuming the x0 coordinate lines are approximately lined up with the material world lines. Now that we've gained a little bit of familiarity with the stress energy momentum tensor, let's return to the Einstein equation. So the Einstein tensor G mu nu equals 8 pi times Newton's constant G over c to the 4th power times the stress energy momentum tensor. Remember, G is constructed from the Riemann tensor, which in turn is constructed from the metric. It involves second derivatives of the metric tensor. So this is a set of differential equations telling us what the metric is for a given matter distribution, T mu nu. Differential equations for the gravitational field G mu nu with matter distribution defined by the stress energy momentum tensor T mu nu. The analog of the Einstein equation in Newtonian gravity is the Poisson equation. Del squared phi equals 4 pi g times mu. So here phi is the gravitational potential, del squared is just the Laplacian operator, g is Newton's constant, and mu is the mass density. My next goal in this lecture is to give you a feel for the connection between the Einstein equation and the Poisson equation of Newtonian gravity. So let me begin by reviewing Newtonian gravity. So we have a mass, say capital M at location capital X, and that's the position vector. Here's a mass little m with position vector little x, and r vector connects these two. It's little x minus big X. And now the force that big M exerts on little m, the gravitational force, is equal to minus Newton's constant little m big M over r squared times r hat, the unit vector formed from r vector. And we can write this gravitational force in terms of a potential. So we can write F grav as minus little m times the gradient of a potential phi, where phi in this case is minus g big M over r. So these equations express the gravitational force on little m in terms of the gradient of phi, where phi is the gravitational potential at this location created by the mass big M. Now if we have more than one mass, say we have capital M1, capital M2, etc., then we simply add the potentials. So the total potential would be minus g m1 over the distance between the mass m1 and the mass little m, so that's the magnitude of the separation vector, little x minus big X1, minus g m2 divided by little x minus big X2, and so forth. And the force on the mass little m due to all these masses is once again given by minus little m times the gradient of this potential. Now what if we have a continuous distribution of masses? So continuous distribution of mass. Well, in this case we let big M, we replace it with the mass per unit volume, the mass density, times d3x. So mu is the mass density. And now the potential is equal to a sum, so the sum is an integral, of minus g times m, but m is mu d3x, divided by the separation between little x and the point big X that has the mass density mu. Okay, and this is that gives the potential at little x. And I can write this a little more neatly as minus big G times the integral d3x, and that's a big X, times mu over little x minus big X magnitude. Now this result for phi satisfies the Poisson equation. So phi satisfies del squared, that's the Laplace operator, acting on phi, equals 4 pi g times the mass density mu. So the solution of the Poisson equation is written here, and you might actually remember this relationship between the Poisson equation and the integral solution better from your studies of electromagnetism, where in that case phi is the electrostatic potential and mu is the charge density. And we have this same relationship, the same Poisson equation, and this is the integral solution. In our case, phi is the gravitational potential due to a mass distribution with mass per unit volume, mu, and the force exerted on a particle, little m, is equal to minus little m times the gradient of that potential. Now let's return to the case of the single mass, big M. So the gravitational potential, Newtonian potential, is minus g m over r, and I'll just set g equal to 1 for the time being. Now, what is the analog of a single mass in general relativity? Recall the Schwarzschild metric. This describes the geometry outside a spherical mass, isolated, non-rotating mass. And the metric is minus 1 minus 2m over r dt squared plus 1 divided by 1 minus 2m over r dr squared plus r squared d theta squared plus sine squared theta d phi squared. Let me abbreviate this factor as d omega squared. That's a common notation and it will save some writing. So the analog of a single mass in Newtonian gravity is the Schwarzschild solution. And what we would like to do is roughly speaking, identify minus m over r as the Newtonian potential. But we need to be a little bit careful before we do that. First of all, notice what we're trying to do is establish a connection between general relativity and Newtonian gravity. So we'll be dealing with weak gravitational fields. That means 2m over r, which is actually, you'll recall that's 2gm over c squared r, is small. So the first thing I want to do is I want to treat this as 1 divided by 1 minus something small and do a series expansion. So we'll simplify this metric a little bit and write it as ds squared equals minus 1 minus 2m over r dt squared plus 1 plus 2m over r. So that's just the first terms in the Taylor expansion of 1 over 1 minus 2m over r times dr squared plus r squared d omega squared. Now the next thing we want to be careful about before we dive in and identify minus m over r as the Newtonian potential is we want to be careful to deal with the ambiguity in this radial coordinate r. Recall that the r coordinate that appears here is the areal radius. So it gives us the usual Newtonian or flat space expression for circumferences and areas of spheres. But it does not define the proper radial distance. It does not define proper radial distance. So what we would like to do is we would like to choose coordinates that are in some sense as close to Newtonian or flat space coordinates as possible. So we have a choice. Do we use the areal radius or do we switch radial coordinates to a coordinate that measures proper radial distance? The answer is that we really need to switch to a radial coordinate that is somewhere in between these two extremes of an areal radius or a proper radial distance. Now, I don't have a simple argument for what that radial coordinate should be, but the non-simple argument comes from a treatment of the Einstein equations in what's called the static weak field limit. So the Einstein equation in the static weak field, or sometimes call it the Newtonian limit, tells us that the metric can be written in the form of -1 plus some function of the spatial coordinates dt squared plus 1 minus this same function f times the metric for flat Euclidean space. And since we're using spherical coordinates, this is dr squared plus r squared d omega squared. So f in this case is a function of r, theta, and phi. So this is the general form for the metric in the Newtonian limit, and we can compare this to the Schwarzschild metric, which is -1 minus 2m over r dt squared, and in the limit of weak gravitational fields, where 2m over r is small, this next term is 1 plus 2m over r dr squared. Then we have r squared d omega squared. Now, to convert this metric into this form, we just need to replace this r coordinate here with r plus m. So with that replacement, then dr is just dr, so we're just shifting r by an amount m. And notice this can be written as r times 1 plus m over r. M over r is small, so this is approximately r. We're not changing the radial coordinate by very much. But when we do that, let's make these replacements in this metric. What we have is -1 minus 2m over the new radial coordinate, but this is already small, so just changing r by a small amount to leading order doesn't change it at all. So similarly in this term, the new and the old radial coordinates are almost the same, so since this term is already small, we can just leave it alone. And dr squared is the same. Now this r squared becomes r plus m quantity squared. Right? So if we expand this, this is really r squared times 1 plus m over r quantity squared. And now since m over r is small, we can Taylor expand that as 1 plus 2m over r and drop the other terms. And now we see that the metric has the desired form. It's -1 minus 2m over r dt squared plus common factor of 1 plus 2m over r all times dr squared plus r squared d omega squared. So this is the Schwarzschild metric in the weak field limit where m over r is small. And it's the analog of the Newtonian single particle m. So we can identify minus m over r as the Newtonian potential. Now, just like in Newtonian gravity, if we wanted to write down the metric for 2 or more masses, so multiple masses, we would just add the potentials, minus m1 over, say, r1, minus m2 over r2, and so forth. And if we have a distribution of mass, we'll just have a general potential, which is a function of the spatial coordinates determined by that mass distribution. So the static weak field metric is ds squared equals minus 1 plus 2 phi dt squared plus 1 minus 2 phi times the spatial metric, dr squared plus r squared d omega squared. So this is of the form of the static weak field metric. You can see that the function that I called f up here is actually minus 2 times the Newtonian potential. And just to be clear, phi in this expression is a function of the spatial coordinates r, theta, and phi. Now I should warn you that this process of superimposing solutions by just adding phi, this only works because we're in the static weak field regime, and the full justification comes from the analysis of the Einstein equations in which they're linearized. So we're really dealing with linearized solutions of the Einstein equations, and they can be superimposed. But in general, Einstein's equations are nonlinear, so if you have two solutions, you can't simply add them to obtain another solution. Now let's take this static weak field metric in terms of the Newtonian potential phi and compute the Einstein tensor. In doing this calculation, it's helpful to restore the factors of c, the speed of light. So there's a c squared here, and there's also, this is actually phi divided by c squared. So the Einstein tensor then can be computed, and in the limit as c goes to infinity, so the Newtonian limit, what we find is the 0, 0 component of the Einstein tensor is 2 times Laplace operator acting on phi, and the other components are approximately 0. Now, if you'll recall from earlier in the lecture, I showed that the stress energy momentum tensor is dominated by the rest mass density. So T00 is the rest mass, and the other components are approximately 0. And this is in the limit in which the matter is slowly moving compared to the speed of light. And actually, if you put in the factors of the speed of light using these coordinates, this turns out to be mu times c to the 4th power. So putting these results together, what does the Einstein equation tell us? Well, the Einstein equation is g mu nu equals 8 pi g over c to the 4th times t mu nu. And these results tell us that only the 0, 0 component is significant, and that is 2 del squared phi equals 8 pi g over c to the 4th power times mass density times c to the 4th. In other words, this is del squared phi equals 4 pi g times mu, Poisson's equation for Newtonian gravity. So this analysis gives you an idea of the connection between Einstein's general relativity and Newtonian gravity. Roughly speaking, the Poisson equation for Newtonian gravity is contained in the 0, 0 component of the Einstein equation, in the limit in which the matter is slowly moving and the gravitational fields are weak. And the other components of the Einstein equations in that limit are not significant. Now, the last thing I'd like to do in this lecture, and this will strengthen the connection between relativity and Newtonian gravity even further, is to look at the geodesic equations. In particular, the geodesic equations for the metric in the static weak field limit. So that's ds squared is minus c squared minus 2 times the Newtonian potential phi dt squared plus 1 plus 2 phi over c squared times the flat space metric dr squared plus r squared d omega squared. And it will be helpful, actually makes things simpler, if we change coordinates and write the flat space metric in Cartesian coordinates as dx squared plus dy squared plus dz squared. So we simply apply the usual coordinate transformation between spherical coordinates r, theta, and phi and Cartesian coordinates x, y, z. And now the Newtonian potential in this case becomes a function of x, y, z rather than r, theta, phi. Now from this metric we can compute the Christoffel symbols, and in the limit as c goes to infinity, we find that the only non-zero Christoffel symbols are gamma x tt, that's equal to the partial with respect to x of phi, gamma y tt is partial with respect to y of phi, and gamma z tt is partial z of phi. Remember, the geodesic equations are x mu double dot plus gamma mu alpha beta x dot alpha x dot beta equals 0. And for a time-like geodesic, the dot denotes partial with respect to the proper time tau. So for this metric in these coordinates, we obtain the following. We have the t component is t double dot plus gamma upper t alpha beta, but notice none of the Christoffel symbols with an upper index t are non-zero, so this is just t double dot equals 0. And for the x, y, and z components, we have x double dot plus gamma upper x lower tt is the only non-zero component. Here that's partial x of phi times t dot squared equals 0. And similarly for y and z, we have y double dot plus partial y phi times t dot squared equals 0, and z double dot plus partial z of phi times t dot squared equals 0. Now what this equation is telling us is that t is a linear function of the proper time tau. In particular, t dot is a constant. And that means we can write these equations. Let's look at this x double dot equation. This is x double dot over t dot squared equals minus partial x of phi. But because t dot is constant, we can write this as 1 over t dot times partial with respect to tau of 1 over t dot partial x with respect to tau equals minus partial x of phi. So the fact that t dot is constant allows us to bring this t dot inside this derivative. And now this is just the derivative of x with respect to t, and this is just derivative with respect to t. So what we have is second derivative of x with respect to t is equal to minus partial x of phi. And of course we can carry out the same calculation for the y and the z components. So this should look familiar by now. If we let x, y, and z, if we denote them by xi, then these equations become second derivative of the Cartesian coordinates xi with respect to t squared equals minus partial I of the Newtonian potential phi. And this is, of course, Newton's second law. If we multiply by the mass of the particle, then this is just mass times acceleration equals the Newtonian force minus m times the gradient of the potential. Newton's second law, which is of course mass times acceleration equals the gravitational force, which is minus m times the gradient of the gravitational potential. In this lecture, I introduced the Einstein equation, and I showed some of the connections between Einstein gravity and Newtonian gravity. So the Einstein equation is g mu nu equals 8 pi g over c to the fourth t mu nu. Of course, the ultimate justification for general relativity doesn't come from its connections to Newtonian gravity, but from experimental tests. And we currently have a strong body of experimental evidence to show that general relativity, and the Einstein equations in particular, correctly model gravitational interactions, at least for a wide variety of physical situations.